Welcome to another session of Engineering Economics 2373. We're going to talk about this week on the techniques of measuring projects again, and we're going to compare present world and future world with internal rate of returns and some of the interactions that they have. First of all, remember that the minimum attractive rate of return would be the rate that you will use to discount the cash flows on your project, and it's related to the financial cost, given the fact that the project can be financed by debt capital or a combination of both. We have covered the alternatives of measuring the value of a project using present worth or future worth or annual worth. Also, we had made a comparison with the internal rate of return. When we calculate the present value with the internal rate of return, sometimes the present value is denoted as net present value. That's why you have it as NPV. And if the net present value or present worth of the project is larger than zero, then the project is accepted as satisfying the standards for the investor. When we compare more than one alternative, we compare the present value. We calculate the present value for each one of the alternatives, and then we select the alternative with the highest present value. And if we have the opportunity to select more than one, then we select every one of those that have a larger than zero present value. To compare projects with the different lifetimes across all the alternatives, there are a few methods. One of them would be to use the same period using minimum common multiple of alternative periods. And however, this could be a little cumbersome because to compute the minimum common multiple could give us an unreasonable answer. For instance, if a project has 7, 11, and 13 years, 3 projects have this lifetime, then the minimum common multiple would exceed 1,000 years, and that's just not feasible to use as a practical solution. Another alternative is to use n years that will not necessarily be equivalent for the lifetime of all the alternatives, and this method is known as a planning horizon based on policies that the company has, and that's probably the most practical way of doing it. So the present world is just bringing each one of the cash flows that happen in any one of the years brought back to the future, to the present, by discounting it by 1 plus I to the negative t. The annual worth is computed this present worth and then analyzing this present worth by multiplying it times A given P, given the internal rate of return and the number of years. And the future worth is to take each one of these cash flows to a particular period in the future, and the way to compute this is considering the compounding effect of receiving the money earlier before that period, that is multiplying it 1 plus I to the n minus t. We have also talked about the internal rate of return. The internal rate of return is the rate that turns the value of the projects to zero. It is called internal because it does not depend on other rates, and you can compute that regardless of the minimum attractive rate of return. However, in practical mathematical solution, there could be more than one real positive internal rate of return, and this would be a drawback. Let's consider an example. Here we have a project with the cash flows occurring on these days, on these periods, so 0, 1, 2, and 3. We have initial investment of $4,000, then we receive $16,400, an additional investment of $22,320, and then we receive back $10,080. So we can compute the present worth of this. If we use the minimum attractive rate of return being 10%, is each one of the cash flow, as we've done in the past, 1 plus the interest rate raised to the t, and then we calculate the sum, and we find the present worth to be $36.06. So far that's fine. We can probably compute the internal rate of return of the project. Remember, we have in Excel the formula IRR, and we just need to select the cash flows occurring there, and the answer that we have is that the internal rate of return is 20%. Well, that looks very fine so far. Now the problem is that the cash flows that we have here are actually solutions that are posted into a polynomial solution, and when we try to solve that equation, we find that we might have more than one solution. So actually, when we compute the present worth given different values for the discount rate, we might get something better to understand. So here is a graph of the present worth of the project discounted at different rates for that series that we just saw. As you can see, correctly, Excel is giving us the internal rate of return to be 20%, but also there is a root at 40%, and then there is yet another one at 50%. So this situation makes it not very practical, not very easy to describe that for an investor that the internal rate of return is at the same time 20%, 40%, and 50%, and therefore the internal rate of return might have limitations when there are changes in the sign of the cash flows in the profile. As you saw in the graph, there are three routes to solve the problem. That is, there are three positions in which the present worth was equal to 0. And the reason why we have three is because there are three changes in the sign of the cash flows. We have a first change between the first and the second cash flow from negative to positive, and then we have another change from positive to negative between the first and the second cash flow, and finally we have a third change in the sign from the second to the third, or from the second year to the third year cash flows. So given this situation, these three changes, we will find three routes, and that would be a problem. A practical way to try to avoid the problems that the internal rate of return creates is to generate a ratio that somehow takes into consideration the dollar obtained back by the dollar invested, and we call this the saving investment ratio. And the way to compute this is depicted in this section of the video. We have here a project in which we have an initial investment of $1,000, and then we have 4 cash flows of $400 when the minimum attractive rate of return is 10%. We can compute the present worth as we have done before, dividing each one of the cash flow by 1 plus the minimum attractive rate of return, all those raised to the t. We add all these cash flows together, and the present worth for this project is $267.94. Well, the saving investment ratio tells us that we could compute the summation of all the positive cash flows together. So what we're going to do is we're going to add just the positive cash flows, and we're going to divide those by the summation of all the negative cash flows in their absolute value. So I can compute the absolute value of the negative cash flows, in this case only the initial investment, and the saving investment ratio would be the ratio between the positive over the negative, and this would be the saving investment ratio, and the value is 1.26. And that ratio, as long as it's larger than 1, it means that we're getting a larger cash flow than what we are spending. So we can compute for the original problem with the internal rate of return a saving investment ratio, and we're going to do that in the next video.